Shalom class, thank you for tuning in. My name is Innocent Mapanda. Welcome to Innocent Mapanda tutorials. In today's lesson we are going to focus on the topic of groups. I have extracted a question from Zimsec November 2021 paper 2, question number 5. It reads, show that the set 0, 1, 2, 3, right, where 0, 1, 2, 3 are the elements of the set, forms a group under addition modulo 4. 7 marks, right? So to show that the set forms a group, we need to prepare what we call the Cayley table or the Latin square. I hope you are following, right? So how do you prepare the Cayley table? When preparing the Cayley table, it's like you are preparing the table, or the outcome table of probability. So I'm going to put 0, 1, 2, and 3 here. Then I put 0, 1, 2, and 3 there. I hope you are following. Right. Under addition modulo 4. So I'm going to combine here using the binary operator addition. I hope you are following. Right. But there is something that I want you to understand about the Cayley table. The outcomes or the elements that we are going to insert in the Cayley table are not allowed to be equal to 4, the given modulo. They are not allowed to exceed 4, the given modulo. So for any number which is equivalent to 4 or for any number which exceeds 4, it must be divided by 4 so that we write the remainder. I hope you are following. Right, so let us start. 0 plus 0, you get 0. 0 plus 1, 1. 0 plus 2, you get 2. 0 plus 3, you get 3. Right? Let me do this so that I align the numbers. Right, I hope you are following. Right, 1 plus 0, you get 1. 1 plus 1, you get 2. 1 plus 2, you get 3. 1 plus 3, you get 4. But remember the rules. The elements inside the Cayley table are not allowed to be equivalent to the given modulo 4 or to exceed 4. So since 1 plus 3 is giving us 4, we have to divide this 4 by the given modulo 4. You get 1, remainder 0. So I'm going to write the remainder, which is 0. I hope you are following, class. Let us move on to the third row. 2 plus 0, you get 2. 2 plus 1, you get 3. 2 plus 2, you get 4. So 4 divided by 4, you get 1, remainder 0. So I'm going to write the remainder here. 2 plus 3, you get 5. So divide 5 by 4, you get 1, remainder 1. Write the remainder here. I hope you are following. We are now moving on to the last row. 3 plus 0, you get 3. 3 plus 1, you get 4. So 4 divided by 4, you get 1, remainder 0. You write the remainder. 3 plus 2, you get 5. 5 divided by 4, it's 1, remainder 1. You write the remainder. 3 plus 3, you get 6. So 6 divided by 4, you get 1, remainder 2. So you write the remainder 2. So this is how you complete the Cayley table. I hope you are following. Right. So how do you then prove that the set forms a group under addition modulo 4? We have what we call axioms. Right? So we have 4 main axioms that are used to prove a group. Right. Let me use the troubleshooter CA I. I hope you are following. This capital letter C represent the axiom closure. This capital letter A represent the axiom associativity. I hope you are following, class. This capital letter I represent identity. And the last capital letter I represent inverse. these are the 4 main axioms used to prove a group. Yes, we have what we call the commutative axiom, right? But when proving the group, we use the 4 main axioms. I hope you are following. So let me start by closure. So we want to test for closure. Closure test. So what is the closure test? Right. For closure, you need to look inside the Cayley table. The outcomes inside the Cayley table must contain elements which are part of the original set. We must not have a new term or a new element which is outside the given set. So you can clearly notice that all the numbers in this Cayley table are members of the original set, and there are no new terms in the Cayley table. It means closure is satisfied. I hope you are following. So for the closure test, you write this. If you take any element, right, A, binary operator of B, you must produce an outcome which is an element of the given set. Hence, closure is satisfied. I hope you are following, class. Right, let me shed more light on the closure test. We have a group G, which is containing the elements 1, 2, and 3. We want to prove that whether or not G forms a group under addition modulo 4. Right. So remember, you prepare the Latin square or the Cayley table. This is 1, 2, 3, and this is 1, 2, 3. Right. So after filling up all the terms, you can clearly notice that closure is not satisfied. Why? Because we have a term which is 0, and 0 is not part of the original set. Hence, the set is not closed. Therefore, G does not form a group under addition modulo 4. So this is what I'm trying to say by closure. The outcomes inside the Latin square, the outcomes inside the Cayley table, right, must be part of the original set. So 0 is a new element. Hence, the set G is not closed. I hope you are following. So I want you to stay tuned as we move on to the next axiom, which is associativity. So after testing for closure, we move on to A, which is associativity. So I'm now writing associativity test. I hope you are following, guys. Right. So for associativity, we use this formula: A, binary operator B, binary operator C. So I'm going to put the first 2 elements inside the bracket. Right. For associativity to be satisfied, this must be equivalent to A, binary operator B, binary operator C, but this time the brackets are now on B and C. I hope you are following. Right. This is the associativity formula. Right. So we would like to choose any 3 elements of our choice from the given set. So the numbers in the given set are 0, 1, 2, and 3. So we can say, let A be 0, let B be 1, let C be 2. I have chosen the first 3 elements inside the given set. Right. So would like to work out the left-hand side. Remember, on the left-hand side, we have A, binary operator B in brackets, binary operator C, where C is outside the bracket. Right. So what is A? A is 0. So we need to find A, binary operator of 1 from the Cayley table. Right. So this is 0, right? And this is 1. So 0, binary operator of 1, you get 1. I hope you are following. So this entire bracket is going to be represented by 1, right? Then I put binary operator. What is C? C is being represented by 2, right? So we now want to find 1 binary operator of 2, right? So this is 1, This is 2. 1 binary operator of 2, you get 3. So on the left hand side, I'm getting 3 as my answer. I hope you are following. So I would like to prove again on the right hand side. For associativity to be satisfied, we must have 3 both sides, right? So I'm going to start. We have a 0 for A, binary operator. Then our B is 1, a binary operator. Then our C is what? Our C is 2, right? Then on the left hand side here, we have a 0 binary operator of 1, binary operator where C is 2. I hope you are following. Right, then on the right hand side we have 0 binary operator of 1, binary operator of 2. So we are going to make use of the BODMAS. You start by simplifying the terms inside the bracket first. So 0 and binary operator, I'm going to keep them so that I start by simplifying this bracket. So from the Cayley table, 1 binary operator of 2, they are giving us 3. So I'm going to write 3 here to represent 1 binary operator of 2. Right. So what is the 0 binary operator of 3? You go back to the table. This is 0. This is 3. They are going to meet at 3. So 0 binary operator of 3, you get 3. Right. So you can clearly notice that the left hand side is now agreeing with the right hand side. Therefore, associativity is satisfied. So you write the conclusion. Since our left hand side is equals to right hand side, associativity is satisfied. Then you are home and dry. I hope you are following. Now right. Moving on to the third axiom. The third axiom is identity test. Would like to test for identity. So I'm going to write here identity test. I hope you are following. Right. So how do you identify the identity element? The identity element is very simple, right? The identity element is a number, right, here on the column, right, which gives, right, the terms, right, as it is in their order in the original set. Remember, the original set is 0, 1, 2, and 3. You can clearly notice that this 0, right, is producing 0, 1, 2, and 3, which are identical in terms of order, right, from the given set. So we can clearly notice that this 0 is an identity element. I hope you are following. But how do you write the formula for identity element? Right. A, right, binary operator, right, identity element, we need to get A. So E is representing a number, right, that adds, right, or that combines any term in the given set to produce the same term, right? So in this case, we can clearly notice that E, the identity element, is being represented by 0. Because if 0 adds all the terms, you produce the same term. Hence, A, binary operator of E is equals to A. Therefore, the number which gives the same result with the A is 0. And 0 is our identity element. I hope you are following. Right. We are now moving on to the final stage, which is the inverse test. I hope you are following, class. Right. For a group to be satisfied, the axiom inverse, right, must be available or must be satisfied. Right. So I'm going to find the inverse of all the numbers in the set, right? So what you need to know is A, binary operator of inverse. You need to get the identity element. This is the formula for inverse test, right? So 0 to the power of minus 1, 1 to the power of minus 1, which is inverse of 1, inverse of 2, and inverse of 3. I'm going to calculate the inverse of all the numbers, right? So to find inverse, it is very easy. Let me give you this troubleshooter. Inverse answers are going to be extracted from the top row. An inverse is a number on the top row which is aligned to the identity element. I hope you are following. So let's say I want to find the inverse of 0. Remember, our identity element is 0. So the number on the top row aligned to 0 is your inverse. So the inverse of this 0 is 0. Why? Because this 0 is aligned to this 0. I hope you are following. So my answer is 0. So if inverse of 0 is 0, we refer to this as self-inverse. This is what we call self-inverse. I hope you are following. Right, we now want to find the inverse of 1. Remember, inverse is a number on this top row which is aligned to the identity element, and our identity element is 0. So I move to the row with 1. The identity element is 0. The number on the top row aligned to 0 is 3. So the inverse of 1 is 3. So I'm going to write 3 for the inverse of 1. And this one is not self-inverse. Then we move on to inverse of 2. 2 is found in the third row, right? And the identity element in the third row, remember, is 0, right? So what is the number aligned to 0 on the top row? The number aligned to this 0 on the top row is 2. Hence, the inverse of 2 is 2. And this one is self-inverse. I hope you are following, class. Then we move on to the last one, which is the inverse of 3. This is 3, right? And this is our identity element 0. And the number on the top row aligned to 0 is 1. So the inverse of 3 is 1. I hope you are following. Since each and every number in the given set is producing the inverse, it means inverse is satisfied. I hope you are following. Inverse is satisfied. I hope you are following. Then after that, you write your conclusion. Since all the 4 main axioms, closure, associativity, identity, and inverse have been satisfied, it clearly shows that the set 0, 1, 2, 3 forms a group under addition modulo 4. I hope you are following. We are now moving on to part B of the question. It reads, show that the group is Abelian. Show that the group is Abelian. Right. To show that the group is Abelian, you need to identify what to call a leading diagonal, right, which forms a reflection, right? So you can clearly notice that 0, 2, 0, and 2, right, those terms which are in the leading diagonal, I hope you are following, right, they are forming a reflection, right? 1 is being reflected with 1, 2 is being reflected by this to form 2, 3 and 3 are being reflected to form 3 and 3, 0, 0, 1 and 1. So there is a reflection which is formed by the leading diagonal, right? So you write your conclusion. Since the leading diagonal is forming a reflection, therefore the group is Abelian. I hope you are following, right? Another property which is used to test Abelian is the axiom commutative, right? For commutative, a binary operator of B must be equal to B binary operator of A. Let's say we choose A as 0, right? And we choose B as 1. We are saying 0 binary operator of 1 must be equivalent to 1 binary operator of 0. So 0 and 1, they are giving us 1. Then 1 binary operator of 0, 1 binary operator, they are also giving us 1. So the commutative property has also been satisfied, which clearly shows that the set, the group is abelian. I hope you are following. Right, we are done with part B. We are now moving on to part C of the question. It reads, write down the subgroups of the group. Right, so we have three main subgroups. The first subgroup that we have is the trivial subgroup. I hope you are following. So what is a trivial subgroup? A trivial subgroup is a group which is made up of the identity element itself. Remember, in this question, the identity element was 0. So the group is going to be made up of 0. This is the trivial subgroup. I hope you are following. Right, after the trivial subgroup, we have what we call the improper subgroup. Right, the improper subgroup is made up of the original group itself, from the fact that the original group is a subset of the group. I hope you are following. G is a subset of G. So for improper subgroup, you just need to give the original set as it is, 0, 1, 2, and 3. Then you are done. I hope you are following. Then, lastly, the third, we have what we call the proper. This is number 1, trivial. Number 2, improper. Then number 3, we have the proper subgroup. Right. So what is a proper subgroup? Right. A proper subgroup is whereby a number combines with itself to produce an identity element. I hope you are following. A number combining itself to produce an identity element. Those numbers, they become part of the proper subgroup. Right. Remember, in our question, the identity element is 0. So you can clearly notice that 0 and 0, they are giving 0, where 0 is an identity element. So this 0 qualifies to be part of the subgroup, proper subgroup. Right. Then another term which qualifies is the 2. 2 binary operator of 2 is giving us 0. 2 binary operator of 2 is giving us 0. Therefore 2 is part of the proper subgroup. Are you there? But 1 and 1, they give you 2, which is not 0. 3 and 3, they give you 2, which is not 0. So we have only 2 numbers that combines themselves to give the identity element, and those numbers are 0 and 2. They formulate what we call the proper subgroup. I hope you are following, class. Right. Then we are now moving on to the last question. Part D, it reads, write down the order of the set. Right. So the order of the set is simple. The order of the set is good as the numbers, the number of elements inside that set. So remember, in the set we have 0, 1, 2, and 3. So the order is 4 because we have 4 terms in that set. I hope you are following, class. Right.